Buffer overflow.
What are we going to do in this video? One, we are going to quickly go over what a buffer overflow is and how it works. We are also going to dive in a little bit so that you know how it happens. Two, we are going to do a buffer overflow on a real program. We are going to get it to execute our own shell code, and we are going to prune the system and get root shell. So let's begin. Good evening, hackers. Welcome back to the channel. If you haven't already, hit that subscribe button so you don't miss out on any more tutorials in the future. Let's begin. So we're going to have a look at the memory of a computer now, and that can change depending on the architecture, as we'll see in a minute, with the high addresses and the low addresses. And then we're going to dive in deeper to the stack, which is where this vulnerability occurs. Okay, so this is the memory layout on your computer. Now, on the right hand side, as you can see, we've got some addresses. We've got 0x, and then we've got a whole row of Fs. And at the bottom, we've got zeros. Fs are the high address, which is the top, and the zeros at the bottom is the bottom. Now, the stack goes towards lower addresses, and the heap is going towards the higher addresses, and we've got that white space in the middle. That's free memory space. Now, depending on the computer architecture, the top and bottom can be switched around basically. So the bottom, the 0, 0, 0, 0, 0 will be at the top, and the F's will be at the bottom. So it depends on your machine architecture. But stack, yeah, usually goes down to smaller addresses basically. So this is the memory layout, and now we're going to dive into the actual stack and take a look at that, getting ready for our buffer overflow. What we have here is some registers, and you can think of the ESP as the top and the EBP as the bottom. And what we have is, if you are sanitizing your buffer correctly, then the data will fill the buffer space and it will go down the stack towards the bottom. Now, if you are not sanitizing the buffer space correctly, then you can actually leak the data through into the EBP and then into the EIP. Now, once it is into the EIP / return address, you will get a segmentation fault. And if you look in GDP, which is a debugging program, as we're going to do in a minute, you can look at the segmentation fault and see what address has been given. Now, the EIP, the instruction pointer / return address, that will take a 4-byte hex number, and basically what that does is that returns to a specific address in the stack to continue executing code. Okay, so we're going to do a practical example, as I think it will help you learn and it will help me explain it whilst I'm going through it. So we're going to jump into a CTF box for this, and we're going to SSH in. So I'll do that now. I'll also leave the username, password and the address on the screen so that you can jump in there yourself. You can mess about with it, and yeah, just mess about with it all day. That's what I've been doing. So we'll do SSH Narnia2, which is the username at narnia.labs.overthewire.org/p for port, then 2226. Nice and easy. Press yes. We'll paste in the password. Now we can just clear that. Don't need that. We can do cd/narnia. Clear that. Now if we do ls, as you can see, we've got some binaries here. Now these are the each levels. We're obviously on Narnia 2, so we go to this one. It's red. That's because it's got if we do ls-l, as we can see, Narnia 2, the group user is Narnia 2, so we can use it, and that means we can just execute it because it's got the X here. But Narnia 3 was the user that created it, so Narnia 3 privileges are to read, and it's got S, which is the set UID. So if we can exploit Narnia 2 binary by overflowing it, running a shell, we can then use the S here and the enhanced privileges, because it's red, to open that shell as Narnia 3, and therefore we can look in Narnia 3's password files and any other folders and files that you normally wouldn't. And that is how the great buffer overflow. So we'll clear that, do ls, and we've got narnia2.c, so we've got the source code. We'll have a little look at that now. So we'll do cat /narnia2.c. Now, as you can see, the script is only small, so it's nice and easy. Now, what we want to look at is we want to look at char, buff, and then 128. So that buffer takes in 128 bytes, and if you remember, chars are 1 byte anyway, so yeah, 128 bytes. Now, second thing we want to look at is string copy. String copy, like so many other functions, if you Google, you find out what they are notorious for allowing buffer overflows. Reason being is they do not sanitize their input. Basically, they allow argv1 to be 200 bytes, say, and it will still, string copy will still copy that 200 bytes into buff. Buff only takes 128 bytes. That means the rest of the bytes will leak and overflow, basically, and that is how we're going to exploit this binary. So we'll just clear that. We'll do /narnia2, and then we'll do the $, because we're going to run Python command as the argument. So $, and then parentheses, and we do Python -c for command. Now we're using Python 2 in this SSH environment, but you could use Python 3. They do have it on here as well. You can look through the box anyway and get some mischief, whatever. But Python -c, and then we want that, and then we'll do that print, and then a, and then we'll do times. It takes in 126 bytes, so if we do 150, then we'll press enter, and we've got a segmentation fault. Okay, that's a good sign. Segmentation fault. That means it has gone past and it has overflowed. So what we're going to do now is we're going to load up GDB, which is a debugger, and we're going to look into it some more. Now that we know a little more about the how the program is supposed to run, let's see what it looks like when run under the right circumstances. One command I like to run is ltrace, which will run the binary until it exits, recording and intercepting the dynamic library calls that are called by the executable. This is not necessary, however, but it will show us some information regarding the memory addresses that are called. Running the executable a few times with ltrace will show us if the memory addresses change, indicating the binary was compiled with ASLR. ASLR stands for Address Space Layout Randomization, which can make it harder to buffer overflow, but not impossible. So, running the executable with and without a command line argument, and we will have a look. So we'll do ltrace, and then we'll do Narnia2. We'll just run it. Okay, as we can see, we've got libc_start main. There's the addresses. Run it a second time and a third time. Have a look at the addresses. Nothing's changed so far. So far so good. Now we'll give it a command. We'll give it a Python command as the argument. So we'll do a $, parentheses. We'll do Python -c. -c is for command. And then we will do print, and then a, and we'll do times 128, and then we'll close that off, enter, and then we'll just run that 3 times, and as we can see, no memory address has changed. So now we know the memory address doesn't change. We supplied exactly 128 A's, so let's step it up and add some more characters and observe. Let's add 140 A's and see what happens. So we'll change that 128 to 140. And as you can see now, great, we got a segmentation fault. And now we need to determine the exact offset to craft our payload. We will use GDB to debug the binary while supplying the characters. So we'll clear this and we'll do GDB -Q, gets rid of the text that pops up when you first start the program. Don't really need it, so Q gets rid of it. And we'll do Narnia 2. Okay. This part is not necessary, but I like to set the disassembly flavor to Intel. So I'm just going to do set disassembly -flavor Intel. Cool. Okay. Now we are going to disassemble main and set a breakpoint at the end of main function. Your memory address may be different, but you'll want to set a breakpoint at the leave operand. So I'm going to do dissas main. So we've got the main function here. You're going to want to set a breakpoint at leave. So you just do B and then the pointer star, whatever it's called, 0x08048449C. So I'm taking the address for leave operand, which is here. Your address may be different, but just set breakpoint at leave. Cool. Breakpoint 1 at, yeah, cool. So with our breakpoint set, we can now run our payload to determine the offset. Knowing the offset is important to know, because we need to know, it's important to know the size of our exploit and knowing where to set the return address. To do this, we're going to supply it with 140 A's and we're going to have 4 B's and see if our B's overwrite the instruction pointer, the EIP register, the return basically. So we will do R for run, and then we'll do the Python again. So Python -C, wait a minute, yeah, Python -C, and then print, and we're going to give it 140 A's, so times 140 plus capital B, and then times 4, and then we close them off. Now in hex, A is 41, so 41 is a capital A and 42 is a capital B. This will be important in a minute, as you'll see. So we're going to run that. We'll press C to continue, and we've got program received signal SIGSEF segmentation fault. We did get that before when we ran it on ltrace, but because we're in the debugger now, we've got some more information. We've actually got the address that was in the instruction pointer, and like I said before, it's 4 bytes, 2 hex characters are 1 byte, and we've got 41, 41, 41, 41. This is A, capital A, capital A, capital A, capital A. So our A's have overflowed from the buffer, and they've overflowed into the instruction pointer, but we need to get the offset right. So we've got 4 B's here, and we're going to lower the A's, and once the B's, which will be 42, once we have 42, 42, 42, 42, we know that our capital B's are in the instruction pointer and we will have the correct offset. So we will send 136 A's and 4 B's, and if that doesn't work, we will continue to reduce our A's until we see our EIP register / instruction pointer / the return. Yeah. So let's do that. So I'm just going to press the up arrow key to cycle through, and we'll change this to 136. Now we're going down in 4s because obviously this takes 4 bytes, so we'll take 4 bytes away from the A's, and hopefully the B's will then be in there. We'll enter, press Y to restart it, and then we'll do C to continue because it hit our breakpoint, and we've still got 41, 41, 41, 41. So we know the A's are still taking up the return address, so we need to take more A's away. So we'll try again, and we'll do 32 A's this time. Y to continue. It's hit our breakpoint. We'll do C to continue, and now we have 42, 42, 42, 42. Now this means that the EIP register is overwritten by our B's. So we now have the correct offset, and we know the size we are working with. So we're going to start creating our exploit now. So we'll move on to that. So exploit development. We have our offset and we know the size we are working with. So let's start crafting our exploit. Consulting http shell-storm.org. We will be using Linux x86 XE CVE /bin/sh shellcode. So we've got our character shellcode here, as you can see, it's in hex format. This shellcode will execute /bin/sh for us and is 25 bytes in size. Taking our payload of 136 A's, the 136 is including the B's, obviously, the A's and the B's. 132 A's, 132 A's, and we've got 4 B's, which is a total of 136. And replace them with a NOP sled. Now a NOP sled in hex is /x 90. And what that does, remember, is when the return address or the instruction pointer hits a NOP sled, it will just move to the right, and it will just keep doing that until it finds our exploit code, and then it will execute our shell code and give us the shell of the next user, root user, whatever. So minus 25 bytes for our shell code and 4 bytes for our EIP, which is for the instruction pointer. The NOP sled is used to direct the CPU's instruction execution flow to a desired destination, in this case our shell code. And that's what we're going to do. So let's move back into the GDP and go from there. Okay, so let's throw our payload at the binary and see what happens. So we'll do R for run, and then paste in the Python command code for the argument. So Python -c print. We got /x90, which is the NOP sled, times 107. Then we've got plus, and then we've got our shell code, which is 25 bytes. So 107 plus 25 is the 132, replacing the capital A. And then we've still got the B, capital B, times 4. So we're going to run this. It will stop at the breakpoint, and then we are going to examine the stack pointer, the ESP, and find a memory address that is filled with /x90, and then we will give our return or our instruction pointer that memory address in those NOP sleds, so that when it gets to the return address, it goes into the NOP sleds. Then it slides through them until it reaches our execution code, our shell code, and then it will execute and hopefully give us the shell. So we'll do that, we'll run that, yep, hit the breakpoint. Now we're going to look at the stack, so we'll do x / and then we'll do 300, and then WX, and then we're going to do the $, and then ESP, press enter, enter again to load it all. Okay, so we've loaded the 300 of the stack. So if we go up here, we can see the 90s. Okay, usually usually that would be fine, but I've actually been trying to record this 5 times now for some reason, and actually I think these 90s may be the wrong ones for some reason, although every time I've done it before it usually starts here, but they actually didn't work, so I actually think that's an old value. I don't know, I think that maybe bugged or something, but yeah, the 90s are actually also down here. So this is the correct one for me. So if it doesn't work first time, maybe have a look and see if there's actually any more on the stack. I don't know if this is here from before or whatever, but anyway, yeah, the 90s are here for me. And obviously we've got the 90s, the NOP sleds, and then we've got our shell code here, and then we've got obviously the 42, 42, 42, and where's the other 42? Here it is here, yep, 42. So they're the B's, okay? And obviously it's little endian, so if we wanted to input, say, if we choose this memory address for the instruction pointer, we cannot just put FFFFD858 because that will go in to where the instruction pointer is, as it will go in as 58D8FFFF. It will go in backwards, so we've got to put that in backwards, because when these go in, this will be inserted, say, into here as FFFFD858. You know what I'm saying? So we're going to put 58 first, then D8. So 58 will go here, which is where it should be, then D8. Yeah, we put it in backwards. So we'll run the code again, and we'll change the B's now to the memory address that we want the instruction pointer /return to go to. So /x, then we'll choose one in the middle of the 90s. So 58. This one here I'm choosing. So x58 /x d8 /x ff and then /xff. Okay, so we ran them off, put the apostrophes in, blah blah. Yeah, all good, parentheses done. So what will happen when we execute this is it will obviously buffer overflow like we did with the A's, NOP sled and our shellcode. It will then go reach into the instruction pointer, and we will give it this memory address. When it buffer overflows into the instruction pointer /return, it will have this 4-byte memory address. It will then go to this memory address, so it will go boop to here, this memory address here. It will then start reading the NOP sleds, and it will just go along the NOP sleds until it comes into contact with our shellcode. It will then execute the shellcode and hopefully give us a shell with higher user privileges. So we're going to run this code now. Press Y, yes. Breakpoint, press C, continue. And cannot access memory address, blah 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 blah. But if we have a look after over here, we've got continuing, and then we've got process 971 is executing new program /bin/dash. So it executed the shell. So we're going to get out of the debugger now. So we're just going to do quit. Yes, we want to quit, clear, and now we will run the code again, but obviously for real this time. We're going to execute the code now for real without the debugger, and hopefully we should get the shell. Press enter, and as we can see, little icon here, and we've got little icon flashing. So we'll do a who am I, and it says Narnia 3. We were obviously using Narnia 2. So now we have got the we've got a higher privileged shell. So now we can go into we can do cat, and then we can do /etc/Narnia_path/Narnia 3, and we've got Narnia 3 password. Yeah, that's how we do buffer overflow. Simple buffer overflow. In the next video we'll be doing string format exploitation in binary files and that. So look forward to that. Stay tuned and goodbye.